Hello and welcome to the presentation. The picture that you are seeing on the screen is familiar to you from the previous video, that it is the PN junction diode which has developed a depletion layer and barrier potential around this junction, the PN junction. Now the next part is to forward bias this PN junction. Biasing can be done in two ways, and one of those ways is forward biasing, and the other one is reverse biasing. We will first see how to make this PN junction diode a forward bias. When an external voltage source is connected to this PN junction with anode connected to the positive terminal of the battery and cathode connected to the negative terminal of the battery, diode gets forward biased. Still, the voltage is not given to this diode. That is why it's as good an unbiased PN junction only with the barrier potential of zero point 0.5 volts. It's an example only. 0.5 volts is an example. Okay. Now, we will see the variation of the voltage between anode and cathode of this diode and the current flowing through this anode and cathode, means the diode, by drawing a graph, two-dimensional graph, taking voltage across this anode and cathode along the x-axis and the forward current of the diode along the y-axis. When the current is flowing from anode to the cathode through the diode, we call it as the forward current. Now, when this external voltage is raised gradually to zero point 0.1 volts, with this 0.1 volts, you can see that in the animation, you can see that there is a reduction in the concentration of the ions at this junction, so that the barrier potential is reduced. Initially, it was mentioned to be having 0.5 volts. With the application of 0.1 volts from the external battery, this barrier potential is reduced to, say now, 0.4 volts. As this external battery is directly opposing the barrier potential is reduced. With this reduction in the barrier potential, a few of the free electrons will be crossing this junction and pass through the P region and reach the positive terminal of the external battery, creating a small current. This small current will be represented by a small red line here at this graph origin. You can observe here. It would be a very small current initially with the application of 0.1 volts. Now, when the battery voltage is again raised to the next new level, say 0.2 volts, again there will be a reduction in the concentration of ions at this junction, reducing the barrier potential to still lower level here. With this barrier potential reduced, there will be the reduction in the opposition to the flow of these free electrons through this junction. With this applied voltage increased, the barrier potential decreased, these electrons are free to move. They are free to cross this junction, creating more current, and in the graph the line reaches the new height, new point representing the increase in the current flowing at this new voltage level. Again, when the applied voltage is still increased, say to 0.3 volts, the barrier potential still collapses to the lower value, say to the 0.2 volts level. With this higher voltage applied, more number of free electrons will be pushed through this N region, and these enforced or these forcibly pushed free electrons will be crossing this collapsed barrier potential and create more current through this anode and cathode region. And the same increment of the current is again represented by the new height of this curve, new location of this curve on the two-dimensional plot, characteristic plot here. By still increasing this external voltage to zero point 0.4 volts, there will be still collapse in this barrier potential and an increment in the forward current of this diode. And when this voltage, external voltage, is raised to say 0.5 volts, this barrier potential is reduced to zero level. When the barrier potential is reduced to zero level, there will be no opposition to the flow of charge carriers at this junction. Means the resistance is brought down to zero value, and the diode is acting like a very good conductor here. With no opposition to the flow of any charge carriers, it acts as a very good conductor. With this applied voltage 0.5 volts, at which this barrier potential is totally reduced to zero, making the resistance of this diode come down to zero, the current can be easily flowing through this diode, and this condition of the diode is called as forward bias condition of the diode. Now, at this particular voltage of the external source, current will be flowing freely through this diode. The same variation is plot in the graph here. If the voltage externally applied by the battery is still increased above this 0.5 volts, more number of free electrons will be passing through this junction diode, making the forward current through this anode and cathode of the diode increase linearly as shown in the graph here. Now we say that the diode is completely forward biased to conduct the current freely with no resistance at the junction. This present condition of the diode is called as the forward bias condition of the diode, and the diode is assumed to be acting like a closed switch when it is forward biased. In the next video, we will see the response of the PN junction when the battery connections are reversed. We will meet you in the next video.